In sterilization, we are attempting to reduce the bioburden. From 10 raised to 6, you bring it down to 10 raised to 5, and then 10 raised to 4, and 10 raised to 3, and so on and so forth. Given a choice, you would like to eliminate the bioburden, but you will see soon that elimination is not a realistic option for the microbiologist. Because 10 raised to 5 can be reduced to 10 raised to 4, and 10 raised to 3, 10 raised to 2, 10 raised to 1, and finally 10 raised to 0. But 10 raised to 0 is 1, it's not 0. 10 raised to 0 can be further reduced to 10 raised to minus 1. But 10 raised to minus 1 is 0.1, it is still more than 0. 10 raised to minus 1 can go down to 10 raised to minus 2, 10 raised to minus 3, 10 raised to minus 4, and so on and so forth. But it's always 0.00000 whatever and 1. It is more than 0. So it is an exponential decay that asymptotically approaches the x-axis and perhaps reaches the x-axis at infinity. Therefore, it's always above 0. It's never 0. That's the reason why in their notation, they do not write CFU equals 0. They say CFU less than 1, implying that they do not want to see any colony forming units recovered in their process. Now, what do you mean? How do you interpret something like 0.1 or 0.01? It sounds like the average number of children in Hyderabad per family is 1.84. Where do you get 1.84? You have one child or you have two children. You don't have 1.84 children. Here, the interpretation is, if the value is 0.01, it means the possibility of a survivor per 100 items treated is 1. In other words, if you have subjected 100 items to your sterilization process, there is a possibility that at the end of that process, there is still 1 possible survivor. This PSI is either probability of surviving item or probability of survival index. Now that we know that you can never have total elimination of the bioburden, there must be some place where you stop, where you weigh the risk versus benefit of the sterilization process and take a call as to how much risk you're willing to live with for the benefit that you get. So to make a process commercially viable and yet keep the patients relatively safe, the regulators have chosen a value of 10 raised to minus 6. A sterility assurance limit of 10 raised to minus 6. In other words, you're giving a sterility assurance of not more than 1 possible survivor per million items that are treated. This is called the SAL, the sterility assurance limit, or the sterility assurance level of your sterilization process. When you set about designing a sterilization cycle, the first thing that you need to know is what is the inactivation factor of the design. Now, what do we mean by the inactivation factor? It is the starting bioburden divided by the residual bioburden at the end of the treatment. So if the starting initial bioburden at time equals 0 is n sub 0, this is divided by the bioburden at the end of the treatment, the residual bioburden, let us say n suffix r. So n0 divided by nr would give you the inactivation factor. But as I said earlier, microbiologists normally work in logarithmic values. Therefore, you talk in terms of how many logarithmic levels you have reduced. For example, if the initial bioburden is 10 raised to 6, and at the end of your sterilization treatment, you are expected to provide a minimum of sterility assurance limit of 10 raised to minus 6, then 10 raised to 6 divided by 10 raised to minus 6 would be the totality of the inactivation factor. In logarithmic terms, it is log of 10 raised to 6 minus log of 10 raised to minus 6. So you have 6 minus minus 6, that comes to 6 plus 6, that is 12. So effectively what you have done is brought about 12 log reductions. Now it is not enough, whatever be the microorganism and whatever be the mode of sterilization treatment, all microorganisms are not equally robust or equally vulnerable to that mode of treatment. Most organisms die off very quickly, but there are those who are spore formers, and the moment the conditions become difficult for them, they go into what they call a spore form. Now once you have a spore, it becomes a little difficult to inactivate or get rid of that spore. Now for each mode of treatment, you have a different organism which has the greatest resistance to elimination by that mode of treatment. For example, if it is moist heat, you have Stereothermophilus. But if it is dry heat, it is Subtilis. So it is not enough to just say, I have a sterilization cycle designed for 12 log reduction. 12 logs of what? So you must choose that spore which has the greatest resistance to that mode of treatment. So you start with 10 raised to 6 of that particular spore and show that your sterilization cycle brings it down to 10 raised to minus 6 of that same spore. So you have what is called 12 spore log reductions, or SLR. As I said, for moist heat, it is Stereothermophilus, and for dry heat, it is Subtilis. Now we go into certain other terms that we should be first familiar with before we design a sterilization cycle. If we were to take 10 raised to 6 as the starting bioburden of a certain spore population and apply a certain treatment to bring down that bioburden level from 10 raised to 6 to 10 raised to 5, in other words, 1 order of magnitude reduction. In other words, 90% of the population, initial population, has been eliminated. So you have 10 raised to 6 coming down to 10 raised to 5. 1 decimal value reduction. How much time does it take for that agent at that level of lethality or concentration to bring about that 1 decimal value reduction in the population? That time is called the D value at that particular concentration level of that particular agent. In other words, for moist heat, we have Stereothermophilus. At 121 degrees centigrade, how much time does it take to reduce Stereothermophilus population from 10 raised to 6 to 10 raised to 5? Now, some manufacturers give you biological indicators with a D value of 1 minute, some give you 1.5 minutes, some give you 2 minutes, some give you 2.5 minutes. It depends on the source, it depends on the strain, but whatever it is, that has been calibrated at the biological indicator manufacturer's end, and he tells you this is the D value of this biological indicator that I am giving you at this particular temperature. Now that we have understood that D value refers to the time for 1 decimal reduction in the original population of the bioburden, how do we determine it? There are ever so many methods that are available, not all of which correspond, but the most popular ones are the fraction negative method, and the other is the survivor curve method. Now, what are the difference in the two methods? In the fraction negative method, you talk about an initial spike of a certain population and check how much of that is inactivated over a period of time. In other words, in the initial stages, the inactivation level is 0, the inactivated population fraction is 0, and then you may have 10% that is inactivated, then 20% inactivated, and finally 100% inactivated. So by finding out the fraction that is negative, that is showing as negative recovery, you then find out the totality of time that it has taken and then determine what is the time for bringing about 1 decimal value reduction. Now, the assumption in this particular method is that the reduction in the population is linear. It may not be. In the survivor curve method, you do the opposite. You talk about a certain spiked value you start with, let's say 10 raised to 6. And over a period of time, you see how much you can recover. In other words, how many are still surviving. And then plot that. Now, if the decay is linear, it will start at 10 raised to 6 and progressively linearly fall. But you might find something very curious. You might find that initially the spores become active and start growing. So 10 raised to 6 starts becoming 10 raised to 7, 10 raised to 8 before the lethality effects start coming into play. And then there is a decline. So after that steady state point, there is a linear fall down. If you were to now extrapolate that line after steady state and see the y-intercept, you might find the apparent y-intercept is not 10 raised to 6. If it is concave upwards, it may be 10 raised to 9. And if it is concave downwards, that is, as soon as you start your treatment, the population decomposes initially, dramatically, and then stabilizes and then falls at a certain linear rate. Now, if you were to extrapolate that and see the y-intercept, it may not be 10 raised to 6, it may apparently be 10 raised to 4. Now, why am I telling you this? You started at 10 raised to 6, and let us say it took you 12 minutes from 10 raised to 6 to 10 raised to minus 6. Now, the fraction negative method would tell you that you've taken 12 minutes to bring about 12 spore log reduction. The d value is 1 minute. But in the survivor curve method, if it is convex upward, the y-intercept is not 10 raised to 6, it is apparently 10 raised to 9. So from 10 raised to 9, you brought it down to 10 raised to minus 6. So you brought about 15 spore log reduction in 12 minutes. That means 12 divided by 15. That is 4 divided by 5. That means d value is 0.8 minutes, not 1 minute. So the fraction negative method overstated the d value instead of 0.8 minutes as 1 minute. Now, if it is concave downwards, the y-intercept appears to be at 10 raised to 4, not 10 raised to 6. So it looks like you have brought a population of 10 raised to 4 down to 10 raised to minus 6. That means you brought about effectively a 10 spore log reduction. Now, this 10 spore log reduction or apparent 10 spore log reduction has come about in 12 minutes. In other words, the d value is 1.2 minutes, not 1 minute. So your fraction negative method understated your d value as 1 minute when it in fact appears to be 1.2 minutes. So this is how you can cross-check in your own laboratory the d value claim made by any biological indicator. Most people don't go through this exercise. They simply accept the certificate of suitability or test certificate given by the biological indicator supplier and then accept it at face value and justify that since he's one of the world's best suppliers of biological indicators, because there are not too many of them, that you are justified on the basis of his reputation and consistency and the fact that the rest of the industry is also buying from the same source, and therefore do not carry out corroborative tests at your end. But if you want to do it, this is the way that you can attempt to do it. The next parameter we should be clear about is the Z value. Now, what is the Z value? If you have a particular lethal agent at a particular concentration level, at a certain dose level. And now at that level, it is taking 100 seconds to bring the population down by 1 decimal value. How much must you change or increase the dose level of that same lethal agent to reduce the time to bring the population down by 1 order of magnitude by a decimal value? In other words, if it has taken 100 seconds at a certain concentration level, how much should I increase this concentration level, the dose level, to reduce the time from 100 seconds to 10 seconds? Now, for moist heat, the Z value is 10 degrees centigrade. In other words, if it takes 100 seconds to bring the population down by 1 order of magnitude at 121 degrees centigrade, then it will take 10 seconds to bring about the same change at 131 degrees centigrade. For Subtilis, there is differences amongst different authors. Some people use the reference temperature as 160 degrees centigrade and say the Z value is 22 degrees centigrade. Others use 170 degrees as the reference temperature, and the Z value they have published is normally 20 degrees centigrade. Now, in addition to D value and Z value, you have one more index called F value. Now, what is F value? F value represents the totality of the lethal energy delivered to the load from start to finish. Now, for example, let us say the D value is 1.5 minutes and you brought about a 12 spore log reduction. So 12 into 1.5 is 18 minutes. In 18 minutes, you have delivered a certain amount of lethal energy to the load. Now, the regulator does not allow you to include the heat up time and the cool down time. But whether you like it or not, as you start heating up, organisms start dying out. And as the temperature is cooling off, organisms continue to die out. So if you start at room temperature and climb to 121 degrees centigrade and hold it there for 18 minutes and then bring it back to room temperature, there is a trapezium that you see. Now, temperature on one axis, because temperature is an index of heat as a parameter that measures the amount of heat energy delivered. So if you have temperature on the y-axis and time on the x-axis, you have a heat up time, holding time, and a cool down time. So you see a trapezium. The area under that trapezium is a measure of the totality of lethal energy delivered to that load. Now, if you were to operate at some other temperature, higher or lower, you have a similar heat up time, a hold time, and then a cool off time. The area under the new trapezium, if it equals the area under the old trapezium, then the two lethal energies delivered at the two different temperatures are the same. The two areas under the two trapezium are equal, means the lethal energy delivered to the load is the same. So if we are speaking about moist heat and the reference temperature is 121 degrees centigrade, the totality of lethal energy required to bring about 12 spore log reduction is referred to as F sub 0 or F naught. At dry heat of 170 degrees centigrade, same. And if you're using that as the reference temperature, the reference lethal energy to bring about 12 spore log reduction is given as F suffix H. Now, these can be mathematically estimated, and the equations are given to you here for moist heat, for dry heat, as well as for dry heat for depyrogenation. For the dry heat depyrogenation, you see two different equations. One at a reference temperature of 250 degrees centigrade, and there the Z value is given as 46.4, and another at a reference temperature of 170, where the Z value is given as 54. That is because the Z value they are referring to for endotoxin is E. coli endotoxin. And different authors have published different values at different temperatures. And some have said as low as 38, some have said as high as 55. So the equations that you see over here are obviously from two different sources. But this is how you estimate. In other words, as you see, there is a summation given. Whenever I say area under the trapezium, it is, in the mathematician's language, the integration of the curve. So you take different sections of the curve and integrate the curve. The area under the curve is determined, and that gives you a measure of the lethal energy.